Good evening, everyone. I am Emertxe from Lendi Institute of Engineering and Technology. During my internship at Emertxe Information Technology, I developed an EV ADAS dashboard using the STM32 F103C8E6 Bluepill, Pixim Lab, and Python. The objective of this project is to simulate an electric vehicle with advanced driver assistance system features. The system monitor vehicle parameters such as speed, battery, charge, motor, temperature, torque, and obstacle distance. It also detects unsafe situations like nearby obstacles, blind spots, and faults. Then displays all this information on a live Python dashboard. This project helped me understand embedded systems, STM32 peripherals, UART communication, sensor interfacing, and real-time data visualization. In the modern electric vehicles continuously generate large amount of sensor data. Drivers and engineers need to monitor speed, battery level, temperature, and safety features simultaneously. Monitoring all these values manually is difficult. My project solved this problem by creating a single dashboard that combines CV monitoring with ADAS safety features, making it easier to observe the vehicle's condition in real time. The complete system has four stages. First are the sensors, which provides inputs such as accelerator position, brake position, motor temperature, and obstacle distance. These inputs are sent to the STM32 Bluetooth. The EV control module calculates speed, torque, battery SOC, and remaining range, while the ADAS module checks for collision warnings, blind spots, and parking assistance. After processing, the STM32 sends telemetry through UART at 1,15,200 baud. Finally, the Python dashboard receives the UART data and displays speed, battery level, obstacle distance, alarms, and fault in real time. Real electric vehicles use wheel speed sensors, radar, cameras, and CAN communication. In my project, I replaced these as expensive components with potentiometers, ultrasonic sensors, UART communication, and a Python dashboard. Although simplified, the working principle remains the same and helps demonstrate how an actual EV monitoring system operates. The project was developed in 9 phases. In first configured the development environment, then set up GPIO, ADC, timers, and UART. Next, I implemented the EV dynamic model, followed by ultrasonic sensor integration, ADAS algorithms, fault handling, UART telemetry, UART shell commands, and finally the Python dashboard. I used STM32 Cube IDE for firmware development and Pixim Lab for hardware simulation. The peripherals configured include TIM1 for the EV update every 10 milliseconds, TIM3 for sensor update for every 100 milliseconds, TIM2 for ultrasonic timing in microseconds, TIM4 for buzzer PWM generation, ADC for reading accelerator, brake, and temperature, UART1 for communication with Python, GPIO pins for LEDs indication collision, blind spotting, and fault conditions. The accelerator, brake, and motor temperature are simulated using potentiometers connected to ADC channels. The ADC converts analog voltage into digital values. The EV control modules uses this value to calculate torque, vehicle speed, battery state of charge, remaining range, and regenerative braking. Different drive modes such as eco, normal, and sport change the vehicle's performance. Three HCSR04 ultrasonic sensors are placed at the front, left, and right of the vehicle. The front sensor detects obstacle for forward collision warn. The left and right sensor detects vehicle in blind spots. When the speed is below 10 km per hour, all three sensors assist in parking. The system also calculates time to collision using distance and vehicle speed. Depending on the calculated values, the alarm level changes from adverse and warning and final critical. The fault module continuously checks whether the motor temperature exceeds 90 degrees centigrade, battery SOC falls below 2%, or a critical collision is detected. If any of these fault occurs, the system sets fault flags, stops the motor torque, changes the vehicle state to fault mode, and turns on the fault LED. Every 100 milliseconds, STM32 sends two telemetry frames. The first frame contains EV information such as speed, battery SOC, torque, motor temperature, range, accelerator, and brake values. The second frame contains ADAS information including front, left, and right obstacle distance, time to collision, collision level, blind spot, status, alarm level, and fault status. Python reads these UART frames and updates the dashboard instantly. The UART shell allows testing without moving sensors. Commands such as speed, SOC, temp, mod, fault, reset, and status helps inject test values directly into the controller. This makes debugging much easier. The dashboard has five sections. A circular speedometer displays vehicle speed. A battery bar shows state of charge and remaining range. A speed graph displays previous speed values. An EV information panel shows torque, accelerator, brake, temperature, alarms, and faults. A bird's eye ADAS view display nearby obstacles and blind spot warnings. Finally, the result is the project successfully achieved real-time speed monitoring, battery monitoring, obstacle detection, blind spot detection, fault handling, UART communication, and Python dashboard visualization. The entire system worked correctly inside Pixim Lab. Now the code explanation is for common.h. This file contains all common libraries, macros, utility functions, and global definitions shared by every module. Instead of writing the definitions repeatedly, every source file includes common.h. Next, EV underscore control.h. This file defines the EV model. It stores speed, torque, battery SOC, motor temperature, regenerative braking, drive mode, and remaining range. The EV control functions continuously update these values based on accelerator and brake inputs. Ultrasonic.h. This file defines the HCSR04 ultrasonic driver. It specifies sensor IDs, trigger pulse width, echo timeout, and distance limits. It also declares functions that measure obstacle distance. Ultrasonic.c. This file generates a 10 microsecond trigger pulses to the sensor, waits for the echo signals, measures the echo during using timer 2, converts the measured time into distance using the speed of sound, and store the calculated distance for the ADAS module. ADAS.h. This file defines the ADAS engine. It stores collision threshold, blind spot limits, time to collision values, and alarm levels. Using sensor data, it determines whether the vehicle is in a safe or dangerous condition. Next, fault.h. This file handles fault management. It checks motor overheating, battery level, and collision status. Whenever a critical fault occurs, it sets fault flags and safely stops the vehicle. Next, UART underscore shell.h. This file creates a command line interface over UART. It also contains a ring buffer for receiving serial commands and processing them without losing incoming data. Next, main.h. This file contains GPIO pins definitions generated by STM32Cube and serves as the hardware configuration file for the project. Now the hardware connections. The STM32 Bluepill is the main controller. The accelerator potentiometer is connected to the PAO, ADC channel 0. The brake potentiometer is connected to PA1, ADC channel 1. The motor temperature potentiometer is connected to PA2. The HCSR04 ultrasonic sensor use separate trigger and echo GPIO pins connected to the STM32. Trigger pin sends a 10 microsecond pulse, while echo pins receive the reflected signal to calculate distance. UART1 use PA9 transmitter and PA10 receiver to communicate with the Python dashboard at 1,15,200 baud. The buzzer is connected to PB9, which outputs a PWM signal generated by TIM4. Status LEDs connected to GPIO pin indicates collision warning, blind spot detection, and fault condition. When the project starts, STM32 initializes all peripherals including GPIO, ADC, timers, UART, and PWM. Every 100 milliseconds, the ADC reads accelerator, brake, and temperature values. At same time, the ultrasonic sensor measures distance around the vehicle. The EV control module processes the sensor value to calculate speed, torque, battery state of charge, range, and regenerative braking. The ADAS module analyzes the obstacle distance to detect collision, blind spots, parking condition, and time to collision. The fault module continuously monitors motor temperature, battery SOC, and collision severity. If any critical condition is detected, it activates fault mode, disables motor torque, and raises alarms. Finally, all proceed information is transmitted to UART to the Python dashboard, where it is displayed in real time using uses graphs, status panels, and a bird's eye ADS view. Now, if decrease front distance, the PCB8 and PCB11 will indicates. Now the battery is 99.8% and the speed is 8 km per hour, and the both vehicles are collide with each other, and the alarm is showing critical. And EV metrics torque 0 nm, accelerator 0%, brake 0%, motor temperature 26.9 degrees centigrade. If we increase PAO 0 and we increase front distance, and also um, now battery is 99.8%, torque is 150 Nm, accelerator 100%, brake 0%, motor temperature 26.9 degrees centigrade. Now the vehicle is far away distance. So alarm detects none. If we increase PA3, the PB11 indicates, and the motor temperature is 108.5 degrees centigrade, and the speed is 9 km per hour. Mode is normal, and the battery is 99.8%. Thank you everyone for your valuable time and attention. I am grateful for the opportunity to present my internship project EV ADAS dashboard using STM32 Google, Pixim Lab and Python. This project has helped me gain practical knowledge in embedded C, STM32 programming, peripheral interfacing, UART communication. It also enhanced my problem solving, debugging, and project development skills. Thank you once again. I hope my presentation has given a clear understanding of this project.